Okay, in this presentation, we're going to look at the first half of a survival analysis question. The survival time after diagnosis T of an individual affected by a certain fatal illness is assumed to be exponentially distributed with a probability density function f of t equals lambda times e to the minus lambda t for t greater than or equal to 0. So this is the PDF there. Now, essentially, I have it sort of bunched up a little bit there, actually, but essentially this should be familiar to you at this stage. If you're familiar with the exponential distribution, you should have seen this already, okay? So just as a quick remark, we're going to be using the exponential numbers a lot in this. So have all the rules and the types of calculations that you might need for exponential numbers be ready in your mind. Show that the probability that an individual survives after the diagnosis for at least a time TO is given by probability of t greater than or equal to TO equals e to the minus lambda TO. TO is just T0 if you want. It's just some unspecified but definite quantity, okay? So essentially this is a straightforward stuff if you're familiar with the probability density functions and so on, and calculating inverse cumulative distribution functions. So this is 1 minus the CDF, essentially. So the probability of t greater than or equal to T0 is the integral, okay, from TO to infinity of the probability density function there. So it's the inverse of the, well, it's actually not the inverse, it's 1 minus it's the complement of the cumulative distribution function. So essentially it's a definite integral. So when we integrate all this, what we should do is end up with minus e to the minus lambda t, where our limits of integration are TO and infinity, okay, and we'll end up with that there. So that should be a fairly straightforward question and sort of dovetailing with the work you probably should have done already with continuous distributions prior to this. But just as a remark, remember that the exponential numbers and exponential functions and logarithms and all that sort of stuff come up a lot in this. So it's a good idea to just sort of have this all sort of clear in your head, all those sort of rules. Okay, so the survival times in days of a group of 12 patients recruited into a study of this illness are given in the table below. Well, actually, it's not a table, it's a list. So this is T1 there. So this person survived for 1,327 days. Second person there, T2, 1,464, all the way up to T12 there. So in this particular study, n is equal to 12. And I will sort of flip back and forth between n equal to 12. That doesn't come out very well. So n is equal to 12. I'll flip back and forth between using n and 12 quite a bit in this. So the question is, obtain the maximum likelihood estimate of lambda. Okay, so when we're dealing with stuff like this, maximum likelihood estimates, it's a good idea to be sort of familiar with all of the theory behind it and so on. Because I'm sort of focusing on a practical sort of level, I'm focusing on tutorial questions. I'm not going to get into the theory, but I have a page shortly afterwards where we can look at a couple of things that you might have to sort of go over for this sort of thing, okay? So MLE estimate of lambda is what we're looking for here. Now, just to sort of start us off, what we have to do here is first off calculate the likelihood function, okay? Now, this is a sort of definition there. It's the sum, sorry, it's not the sum, it's the product of all of the PDFs, the probability density functions evaluated for each of these here, all these durations here, okay? So when I break it out like this looks fairly complicated. I think that people are not as familiar with the product function as they are with the summation function. So essentially what we have here is that we can break it up into parts. It's the product of the PDF for the first patient times the PDF for the second patient all the way down there, okay, to the 12th patient there, okay. And in each case, it's the PDF is e to the minus lambda T1, T2, and so on times lambda, okay. So what I'm going to do here is we have lambda in each of these 12 cases there, okay. So what I'm going to do is in each of these 12 cases, or n cases here, that they're just sort of going to combine here as lambda to the power of n. Okay, so what I have left here is e to the minus lambda t1 times e to the minus lambda t2, and so on. So essentially, this is the laws of exponentials come in. E times e to the a times e to the b is equal to e times a plus b. I nearly messed that up there, but so have those sort of things clear in your mind. So essentially what I'm doing here is I'm combining this term, all the way up to this term into this here. Okay. Now I get that it's a little bit hard to read. So what I've done here is I just slightly altered the notation there. So it's the exponential there. It's essentially the same thing there. So just to sort of made the notation a little bit easier to read there. But essentially, this expression here is just this expression here, just with very similar but different notation. Okay, so what we have there is the product of two terms. Okay, lambda n, that's the first term, and the exponential of minus lambda times the summation of all the t terms, that's the second term. Okay, so essentially what we have there is the product of two terms, and we're going to get the logarithm that shortly. So it just pays to take a moment there to just sort of go over logarithm laws. Okay, now here is a is any base, so log to the base a of x times y is log to the base a times x plus log to the base a times y. We're going to use that here. Okay, log of the base a times of base a of x to the power of k can be just rewritten as k times log to the base a of x. We're going to use that for this one. And log to the base e, which is the natural log in other words, okay, of e to the x is simply x. So we're going to use that for this part here, okay. So the next step is to calculate the log likelihood, okay, which is the natural log of the likelihood, okay, which we've just calculated. So we have two terms that are essentially a term that's a product of two terms. So the first term is finding the natural log of lambda to the power of n. Essentially, we can just state it that using the second of those rules that I've just mentioned. And then the second term is the exponential of lambda times that summation there. And we get the natural log of that. It's essentially what we end up is minus lambda times the summation. Okay. So let's just go check back there. Now that minus pops out here because what we're doing there is actually adding that should be, in the first instance, it's a plus, but what we're doing here is because it is a minus sign here, it's plus times a minus, so that essentially just becomes a minus here. That minus there is just, essentially we're adding a positive number and a negative number, if you get me. Okay. Now, just let's fill in all the numbers there. So the summation of all of those durations, of all of those times that we, of all the patient survival times, that was 6,028. Okay, so that's this term here. It's essentially just calculate add up all the durations there. So that is 6,028 times lambda. N times the log of lambda is essentially equivalent to 12 times the log of lambda. So what we have to do is essentially optimize this by essentially determining the maximum using differentiation. So we differentiate it with respect to lambda. So that should not be t, that should be lambda. So when we do that, 12 times log of lambda is simply 12 over lambda, or 12 times 1 over lambda. Lambda here just is essentially what we have there. When we differentiate that with respect to lambda, we end up with 6,028. So essentially what happens is we optimize it when we have to find out what value will give, what value will equal, what value of lambda will let that equal to 0. So essentially we just have to rearrange it algebraically to get the hat lambda, which is the maximum essentially, and essentially that is rearranging this expression here. We get 12 over 6,028, which is a very, very small number there, 0.001991. Okay, that's how it is done. Now, what I'm going to this is essentially what I'm going to use here. Don't read it really. Essentially what I'm going to just remark upon is that there's a lot of theory coming up. So essentially what I'm going to sort of say is there's likelihoods, there's log likelihoods, there's MLEs, okay, and so on. And there's this thing called the Fisher information and so on. And essentially what we're doing here is we are getting a second derivative of the PDF, okay. So essentially what we do here is that it is essentially, this is an important term here. This is the Fisher information. Now, essentially what we're doing there is we are getting the second derivative of the log of the PDF. Okay, and that gives us our Fisher information. Now, it's actually correctly the expected value of that, and I'm going to leave that E term in there, but really, we don't really need it. And okay, so, but I'll just leave it in there for this, for the sake of consistency, so when you check with textbooks and so on. Now, essentially what we're also going to do here is just actually calculate the variance of this. So the variance is simply 1 over the Fisher information there, okay? So that's the variance that we're looking for, okay? So essentially the big part, what we're looking at here really, the big part of what's coming up now is minus the second derivative of the log of the PDF, okay? And then get the reciprocal of that, okay? So essentially, this is just a quick, super quick rundown of all the theory stuff that you should really have in your mind, and probably you might even like read that carefully and you spot some typos and stuff like that. And I apologize for that. It's just really, just very quickly, sort of help you find where you need to be, where you need to look this stuff up in textbooks. I'm sort of focusing on tutorial type questions here. So obtain an approximate value for the variance of the MLE estimate of lambda. Okay, so essentially what we're doing here is calculating the Fisher information. So in the first instance, let's get the second derivative of the log of the likelihood. Okay, now we actually just previously got we started this calculation. We got the first derivative already in the last part. So essentially what we're going to do is differentiate again with respect to lambda, and we get minus 12 over lambda squared. Okay, so the Fisher information is essentially the expected value of minus that. So again the expected value is not a huge part of this really. So at a practical level, just minus whatever you got there. So we get 12 over lambda squared, and the variance is approximated by 1 over of the Fisher information, which is lambda squared over 12. Okay, that's it there. Now there's a third part, another part to this question, but I'll probably leave it there because this is very long now.